Always, sometimes, never. Here we want to decide if matrix multiplication distributes over matrix addition. And I again believe from some of the examples that we looked at, we know that at least it's sometimes true. And I'd like to see if I can prove if it's always true. So I'm going to use the same strategy that I have been. And I'm going to try to look at each side of this equation separately on scratch paper to see if then I can come up with a formal argument. So first, I decided to look at I guess I didn't necessarily do this one first, but it doesn't really matter which one I did first. Let's do it the way I really did it. If I looked at A times the quantity B plus C, and I tried to decide how that might simplify, I decided one of the other strategies that I like to use often is partition. I like to partition the second matrix because this is matrix A times the matrix which is found by taking B plus C. So I usually take this second matrix and I partition it into columns. And so that was my strategy. I first partitioned both B and C into columns, and that would mean that I'm taking A times the result of taking matrix B that I could write as its columns B sub 0 out to B sub n minus 1 since it had n columns. And then partitioning C, I could write it as C sub 0 out to C sub n minus 1 for each of its n columns. And I know how to add matrices. What I need to do is I just need to add their corresponding columns. And so B plus C is found to have a first column that contains the entries in the B sub 0 plus C sub 0. This is our vectors of the same size. And the last column is B sub n minus 1 plus C sub n minus 1. Now, I partitioned this because I know matrix multiplication can be done by partitioning into columns, and the result will be that the first column of my product is the matrix A times the first column of B plus C. So this is first column will be found by taking matrix times this vector, matrix vector operation. And in fact, all of the columns will be found by taking the product of matrix A with the column that is the sum of B plus C. So the last one will look like A times the vector that's found by taking the column of matrix B plus the column of matrix C. Now, what do I know? I know that matrix vector multiplication is distributed. So if I look at A times the quantity B sub 0 plus C sub 0, that's A times B sub 0 plus A times C sub 0, and so forth. All of the vectors we can distribute A times the corresponding vector in B plus A times the corresponding vector in C because of matrix vector multiplication being distributed. Now, let's go back and look at what the other value would be if I try to simplify on scratch paper AB plus AC. Well, again, I'm going to partition by columns. And so I'm going to write B as the matrix with column vectors b sub 0 out to b sub n minus 1, and C, same as I did before, the matrix with columns c sub 0 out to c sub n minus 1. But I know by partition matrix multiply that this product is just A times each one of the columns of B, and this product is going to be A times each one of the columns of C. Okay, now each of these are now just column vectors, and so I have a matrix that has been partitioned into columns here and here. And so I know how to add two matrices that have been partitioned this way. I take the first column of each and add them together, the second columns and add them together, and so forth, the last columns and add them together. Okay, but where am I? That looks very familiar. Isn't that exactly the same as I had just looked at? So if I compare my results, when I simplified A times B plus A times C, and when I simplified A times the quantity B plus C, I ended up with the same representation. And so now I'm ready to do my formal proof. I know this is always true. And so with my proof, what I'm going to do is I'm going to start with one side and show that it's equal to the other side. I'll start with the left-hand side. A times the quantity B plus C. And again, I'm going to partition my matrices. So I'm going to write it as A times, I'll partition B into columns. So the columns are going to look like B sub 0, B sub 1, and so forth, B sub n minus 1, since B is supposed to have n columns. Then I add to it the matrix C that also has n columns, otherwise we would not be able to add B and C. And then I'm going to say by matrix addition, this is A times the matrix with columns B sub 0 plus C sub 0 will be my first column. The second column will be B sub 1 plus C sub 1, and so forth. The last column is found by adding the last column of B with the last column of C, so I can write it as B sub n minus 1 plus C sub n minus 1. Now, if by matrix multiplication, if I partitioned into columns, I can write this as the matrix that with columns resulting from multiplying A times each one of the columns. Matrix vector multiply will give me each one of the columns of the product of A with the other matrix. So the first column is found by taking A times B sub 0 plus C sub 0. And the second would be A times B sub 1 plus C sub 1, and so forth. All of them are found by taking A times the vector representing that column. So the last one will be A times b sub n minus 1 plus c sub n minus 1. Now, these are vectors. A is a matrix, so we have matrix vector multiplies that need to be performed in order to figure out what the resulting matrix will be. But by matrix vector multiplies, we've proven in the past that A distributes over, so multiplication distributes over vector addition. And so this is equivalent to a matrix with, well, this column vector is equivalent to A times B sub 0 plus A times C sub 0. And so forth. All of the columns A will distribute. So the last column will be A times the vector b sub n minus 1 plus A times the vector c sub n minus 1. Now I'm going to work my way backwards. If I want, I could peek at my scratch. And here I want to work my way backwards. And so I notice from matrix addition I could separate, and then I could partition and so forth. So here what I'm going to say is by addition I can actually write this as the matrix with columns A sub B sub times B sub 0 and so forth, A B sub n minus 1 plus the matrix A C sub 0 out to A C sub n minus 1. But now this by partition matrix matrix multiplication I can actually write it as A times the partitioned matrix, but I can skip a step and just write it as A times B plus, again, A times the partition matrix with columns C sub 0 out to C sub n minus 1, but I can skip a step and write it as A times C. But that means that it is true, because the important step here was knowing that matrix vector operations were distributive. We've now shown that matrix operations distribute. So multiplication distributes over addition. And so it is always true that A times the quantity B plus C is A times B plus A times C.